Okay, so today's lecture is on quantum computing. Quantum computing means many different things, and computing itself is one of those things. So, if you had a quantum computer, what algorithms you would run on them, and that is often also referred to as quantum information. And really hope that when we get those quantum computers, then we stop being harassed by pop-up windows like this. In fact, that's why we're working on them, so this doesn't happen. Algorithms of quantum computers are different from classical computers. It's not only because quantum information can be stored in superpositions of eigenstates of quantum systems, and computation goes by creating entangled states between multiple quantum systems. But it's because algorithms that are being used can enable you to solve problems that classical computers cannot solve. And it's not just about being faster, it's about being exponentially faster for certain problems. So certain classes of problems can become easier to solve. So in this sense, quantum computer is a fairly limited device. It's not going to replace regular computers completely, but it can find its own applications. And one area of applications that would be close to you after being in this course for almost a semester is to emulate complex quantum systems like solid-state systems. So, for example, you have a lattice of spins that are interacting, like in the Hubbard model. This model is actually impossible to solve on a classical computer. So that's an example right there, Hubbard model. Solving a Hubbard model can be done on a quantum computer. And if we do that, maybe we unlock a key to major advances such as high temperature superconductivity reaching into room temperature. Right? So this could be the payback for society for trying to build a quantum computer. Also, there's a lot of science and technology that surrounds quantum computing, and as a result of that, a large fraction of modern solid-state physics is, in one way or another, aimed at these kind of quantum technologies where superpositions and entanglement between single quantum degrees of freedom are the focus. Okay? So not only to build a full quantum computer, but to build some quantum devices, quantum sensors, where entanglement enhances the sensitivity of some quantum sensor, and so on. So we are going to talk about these kind of hardware quantum computing today. Okay? But principles of computation, we will discuss them in a concept of, if one wanted to build a quantum computer, what would one have to do? Rather than if one had a quantum computer, what kind of algorithm would one write? Right? So, okay, so pretty much we will follow these famous criteria called DiVincenzo criteria, after David DiVincenzo, whose picture is right there. And these criteria, they tell you what you have to do to build a quantum computer. And there are about 5 major ones, and then there are extended DiVincenzo criteria, which we're going to go through. So first of all, you need qubits. What are qubits? Who can tell me? What does qubit stand for?
Quantum bit.
Quantum bit, right? So as opposed to a classical bit, which is a CMOS based, typically it's a CMOS, remember CMOS? Complementary metal oxide semiconductor structure, where about 1,000 charges or more are stored on an island, and that's a state 1, and if they're not on an island of a semiconductor, that's a state 0. Here, we need to have not 1,000 of electrons, but a single electron or a single degree of freedom that can have two states, like spin up and spin down. We call these states 0 and 1, and we should be able to have a lot of them. So this system has to be scalable. So two-level systems that are also, can be scaled up to, so we can have 1,000 of them, 1,000,000 of them, and so on. Okay, then the second DiVincenzo criteria is about initialization of a quantum computer. You need to be able to prepare it in a known state. This state, the easiest one to talk about is a state where all the qubits are in a state 0. 0, 0, 0, 0, 0, 0, 0, 1,000 zeros, so a state like this. 0, 0, 0, 0, 0. As many zeros as you have qubits. That's the initial state. And then that's because all quantum algorithms can be run by starting in a known state and then manipulating all the qubits according to the algorithm that you choose. Okay, so they all start from the initial state. But then, of course, we want to be able to prepare any state, any quantum superposition of qubit states and also entangled states. So for that reason, we need to have qubit gates. Gates are operations on qubits. So, for example, you take one qubit and move it from state 0, the ground state, to a superposition, 0 plus 1. That would be a gate, acting on a single qubit. And so we have these single qubit gates, which are called U gates, U1, U2, U3. Those are some kind of operations by external fields, by some kind of influence, acting on individual qubits. And now we also need to take the full advantage of the power of quantum computing. We need 2 qubit gates, and that's all we need. So that's the good news. We don't need 3 qubit gates or 5 qubit gates. We can build all other manipulations of qubits out of single qubit gates and 2 qubit gates. Okay? So 2 qubit gates are denoted by these two-way arrows here, and basically what they are is they let you manipulate one qubit based on the state of the other, right? So it's some kind of conditional gates like C naught, conditional not, for example. We're going to look at a couple of examples of such gates. And what you get as a result of these kind of U gates, you can get superpositions of single qubit states. And as a result of 2 qubit gates, you can get entangled states. Does anybody know what entangled states are? What is the definition?
It's a superposition of 2 different states?
Well, that's just a superposition. So entangled states are states in which we cannot factor this state into the states of individual qubits. Okay? So that's mathematically what entangled state is. So here is a 0, 0 plus 1, 1. I cannot say that one of the qubits is in a well-defined state here. So here is another example. Here is a state 0, 1 plus 0, 0. This is not an entangled state because I can write it like this. First qubit in a state 0. Whatever we do, first qubit is in a state 0. Second qubit is in a state 1 plus 0. And here I factored the state of 2 qubits into state of 1 qubit and the state of the other qubit. And this is not an entangled state, right? And this state 0, 0 plus 1, 1 is an entangled state because I cannot do this. And what is the importance of factoring? The importance of factoring is that 2 qubits can be measured independently, and we can get separate answers for them, which are independent of each other, not correlated, and so on. And with the entangled state, the answer depends on what the state of the other qubit is. So, for example, if I measure the left qubit, I will get a 0. I know that the other qubit has to be in a 0 state as well. There are no other options here. Okay. And so this entanglement is responsible for this exponential speed up eventually of a quantum computer. So this is a key property of a quantum computer. And of course, to get exponential speed up, you need to entangle more than 2 qubits. To really see the exponential speed up, you need to entangle thousands of qubits. But you can do that by 2 qubit operations. Okay. So that's all you need. Then another thing you need is readout. So of course, you need to be able to eventually tell what state each qubit is in, because that will be the answer of the algorithm that you ran. Okay. So this two-level system must be interrogatable by something external to the system, like a meter, a field, another qubit, which is a probe. So if you have a system which is a two-level system but doesn't couple to anything outside of it, that is not a very useful qubit, because we need to be able to read out the state of the qubit. And with this comes a problem known as decoherence. And so decoherence is loss of quantum information. And what you can understand it as is you prepare the superposition of 0 plus 1, but after a time, you find the system in a state 0 again, in the initial state. So you try to create some complex state with entanglements and superpositions so that you could run your quantum algorithm, but system tends to relax back into the ground state. And this happens due to coupling to environment, coupling to classical fields around the qubits, or coupling between qubits and some kind of degrees of freedom in the environment, like other electrons in a semiconductor that are flying around and that are not part of your quantum computer, or something like this. And so another criterion is that decoherence has to be sufficiently low to allow a certain number of single and double qubit gates to be carried out during the time of decoherence. So sometimes people say 10,000 single qubit operations during decoherence time is one of the thresholds that people put forward. Okay. The reason for this particular threshold is that there are certain algorithms where if you can do 10,000 gates, then you can correct a single error that occurs due to decoherence. So if you can squeeze in 10,000, then you can fix one of the qubits that decohered and bring it back into the fold for the computation. Okay. And error correction algorithms are also being run on classical computers. So this is not something very special to quantum computers. It's just that the tolerances and the thresholds are much tighter for quantum computers, because each bit is a single quantum degree of freedom, whereas in a classical computer it's thousands of, let's say, charge states. So they're very easy to distinguish. Okay. There are, those are the 5 main criteria, but then you can also imagine that you have a quantum processor in one part of the universe, another quantum processor in another part of the universe, which could be on the same chip, by the way, just a little bit far apart. And to run a serious algorithm or to exchange quantum information, you also need some kind of flying qubits. So you need to be able to transpond a superposition or even an entangled state over a finite distance. And this, from the hardware point of view, is a very different challenge than operating this kind of a local circuit. Right? And this, many architectures for quantum computers require such long distance communication, even if it's on a single chip, but still it's a distance that is longer than the distance of 2 interacting quantum systems, like 2 interacting electrons sitting next to each other, for example. So there's a larger distance communication. And so what could be flying qubits? Well, for example, photons. Photons can retain their coherence, can retain their superposition state for miles and miles. So that's a very convenient. But then you need some kind of a conversion between the quantum state of a local qubit, which is some kind of a electron or an atom or an artificial atom like a quantum dot or a superconducting loop, and a photon. There has to be some kind of a conversion, so some kind of coupling. And so some of the technology is dedicated to these couplings. That's called hybrid systems, hybrids between two different quantum systems which are coupled in a certain way. Okay. So here are two examples of popular two-level systems considered for quantum computing. Both have advantages and disadvantages. So maybe the good approach is to combine the best of several options. For example, spin 1/2 is a natural two-level system. In fact, a lot of the qubit language uses spin 1/2 nomenclature, even if the actual qubit is very far from spin 1/2. So we can still use spin language like those of block spheres that I already mentioned to you before, and I'll show you again, for any kind of qubit, for any kind of two-level system. Photon polarization, you can make superpositions of vertically and horizontally polarized photons. The challenge with photons is to keep them in place, right? So they're really bad standing qubits. If you want to do computation with photons, you have to kind of travel with your quantum computer at the speed of light as they interact and get entangled and so on. Or you have to build a very complicated optical circuit where your algorithm is taking place. But they are excellent flying qubits. So if you want to send your quantum information long distance and not worry about decoherence, that's great. But actually some of the qubits that are doing actually better than these two, better than just spin and better than just photon, look like this. They are very complicated quantum systems, which in some approximation can serve as two-level systems. So for example, here is a single ion of calcium, which is trapped in some electrostatic trap in ultra-high vacuum. And this is the energy level diagram of that system. I believe these two levels in this diagram are the two states 0 and 1 of a qubit. Okay. Actually, I might be wrong. Maybe it's some other two-level system. Maybe you can define different qubits based on the same ion. It depends on what people find more convenient. But then you use different laser fields that are resonant with different levels for control and readout of this kind of qubit. And so this is one of the systems that does extremely well right now. Okay. Ions in electrostatic traps. Here is another very successful type of qubit. It is a squid. So I already mentioned squids to you, and you're going to have a full lecture on squids next week. But a squid is a ring of superconductor, right, interrupted by some Josephson junctions. And what are the states of 0 and 1? They are some energy levels of that system. So the lowest energy levels of that system. Conceptually, you can visualize it as current flowing clockwise and counterclockwise in a squid loop, in a superconducting loop. So you can actually create a superposition of an electrical current flowing clockwise and counterclockwise in a superconducting loop, and then the two states will be current flowing clockwise, flux pointing up, current flowing counterclockwise, flux pointing down. There are many different versions of these qubits, but this particular one is maybe the closest to the conceptual picture that I just told you about. It is called a flux qubit. And so flux in this loop is what, it's flux in this little loop down here, and this bigger loop is the readout. So one of the loops reads out the flux in the other And so this unit has the qubit right here and the readout right here, integrated into one superconducting circuit. Okay. So this is how a quantum computer might look like if you poll physicists working on it today. Many of them will say that this is maybe the most promising at the moment, but it also might look like this or like this. And to make things more complicated, people are finding that there are some benefits to encoding a single qubit in more complicated quantum states. So you can see that the hardware is already fairly complicated because of these multiple levels here or multiple levels in a squid loop. But then also people take multiple qubits and combine them to define a single qubit. So here are some examples of states of 2 qubits which are exchange coupled, and they define 2 states, 0 and 1, combined out of states of 2 physical quantum levels, quantum systems, right? So like 2 different spins or 2 different squid loops define a single qubit. And there are some advantages from the point of view of decoherence because you can define these levels, 0 and 1, to be at exact same energy. And then the relaxation from one to the other is minimized because they have the same energy. So it's like, relaxation is like falling down from a step, from a cliff. And so if they are the same energy, then there is nowhere to fall. So there are some benefits to it. Or even defining some very complicated states of 3 different physical quantum systems. So each of these is a 2-level system. Here is the first one, here is the second one, and here is the third one factored out there. And this has some benefits. For example, if you combine 3 spins like this, then you can manipulate a qubit made out of 3 spins with just electrical fields, where you bring electrons closer and farther apart, and you don't need any magnetic fields. And that has some advantages for technology, right? So people are thinking about these kind of more complicated states to define a single qubit. And at the end of the lecture, if we have time, I will show you sort of the scary truth about what actually people are thinking could be viable qubits. And they go not just 2 or 3 physical qubit states, but they are thousands of physical qubits for one logical qubit. Okay, then people talk about logical qubits. This would be a logical qubit made out of 3 physical qubits. Okay. But okay, let's start slowly and comfortably. How can we initialize a system in the known state, right? So this is one of the DiVincenzo criteria to prepare a known state, and it turns out that 0, 0, 0, 0 is a very convenient state to prepare. All you need to do is wait. You wait long enough, relaxation and decoherence takes care of this. So you wait until all the excitations are gone from the system, and you're going to find it in the ground state. So you just take advantage of the Boltzmann factor. You want a lower temperature, low enough, such that this Boltzmann factor is very small. And the probability of occupying state 1 is very, very low. And then you wait a bit longer, let the system emit energy into the environment, and don't let it get back any energy, and you are in the state 0, 0, 0. And this is, people talk about fidelities in this sense. So a fidelity of 0.99999 means that out of 10,000 qubits, 1 can be in the excited state, and all the others have to be in the ground state of 0. And by some measure, this is good enough to run a quantum algorithm. And so this requires the energy difference between the 0 and 1 states to be about 10 times the Boltzmann energy, right? Kbt. So you just need to be at, your qubit spacing needs to be 10 times the temperature. in the energy equivalent. So for example, if you want to build your qubit out of single atoms, which are naturally quantum systems, right? And there, the energy spacing between the atomic orbitals is of the order of the electron volt. Then you just can be at room temperature with your atoms. You already have a quantum computer. Or you can initialize it anyways. Right? But if you're talking about spins of electrons, and you put these electrons in a sizable magnetic field like a Tesla, which is at a scale that our superconducting magnets can give us, then the energy splitting, which is g mu b for 1 Tesla for a spin 1/2 particle, is hundreds of micro electron volts, so much, much smaller. And you need to be at a much lower temperature, at millikelvin temperatures, to run a quantum computer based on the spins of electrons. Okay? So that you can initialize it by this equilibration to ground state, by just waiting. Okay? And obviously, the farther away you are from these criteria, the lower your fidelity is going to be, and also you might have to wait quite a while if your relaxation time is long. So that's maybe not always convenient to wait. You run an algorithm and then walk away, have a coffee while your quantum computer reinitializes for another try. So there are other ways to initialize a qubit. So for example, if it's a spin qubit, you could put a ferromagnet, make it inside a ferromagnet, or turn on a ferromagnet somehow, and then exchange coupling of all the interactions between electrons will polarize all the spins in the same direction. Right? You can take advantage of some kind of interaction effects. There are techniques for laser cooling, which means you apply a tone, an radiation at the energy difference, which is slightly smaller than the energy spacing between 0 and 1. And by this method, you actually force the system to emit a photon and drive it into the ground state this way. Optical pumping is another optical technique, but here is an interesting approach. It basically uses some of the quantum algorithms to initialize the system. So you perform a bunch of single and double qubit gates, and you project the system by measuring it. Right? When you measure, you can get an answer of 0 or 1, and you can sort of adjust this algorithm in such a way that you would get, with higher probability, a certain measurement outcome. Or you can throw out the instances when you got 1, and the instances when you got 0, you proceed with those for future computation. So you use the process of measuring to initialize the system in the state that you want. Okay? So this can be faster than waiting. But let's say you have an initialized quantum computer, and you start with this state 0, 0, 0, 0, 0. Then what do you do next? You perform these single and double qubit gates. And single gates are like spin rotations. So you have to think back to precession of spins. You apply external fields to a spin, and then all the states of a qubit or a spin are represented on this block sphere, where the poles are 0 and 1, and x and y are 0 plus 1 and 0 minus 1 superpositions with the exact same weight, 0 and 1 of the exact same weight, and then all the other states on the sphere are superpositions with different weight of 0 and 1. So obviously, if you go to the North Pole, you're more in the state with a heavier weight in 0. If you go to the South Pole, you're in the state with a heavier weight in 1. And for spin, this is exact description, block sphere, you can put spin up and spin down on the poles, but you can take any two-level system and the math will be exactly the same. It will always be a block sphere. The physical implementation will differ, and so will the field that makes this qubit spin, right? That makes this spin precess. So for spin, it is a magnetic field, but for an atom, it can be some laser field, and for a charge-based qubit, it can be an electric field. Okay, so these kind of precessions are the foundation for single qubit rotations, and 2 qubit gates are all based on creating entanglement. Okay. So I already told you what entanglement is. Basically, this is an unentangled state. So the left qubit and the right qubit can be factored. And then I do some kind of manipulation on it, and I get this entangled state where I cannot measure individually the 2 qubits and get independent outcomes. The measurement becomes correlated between the left and the right qubits. So 2 qubit gates are often described by these kind of tables. I think I have a full example in the coming slides, but basically here, based on the input, so 2 qubits go into this kind of gate operation by being both in the 0 state, then they come out at 0. But if the left qubit is in the 1 state, then the right qubit flips. Okay, so there is a conditional process happening here. So how to implement it physically, we will see in a moment. But obviously, there needs to be some coupling between the two-level systems to enable this kind of process. Okay, so back to single qubit gates. It is based on electron spin resonance technique, and electron spin resonance involves, like we already discussed before, I believe, 2 different fields. There is a steady, constant field, which we will point in the z direction. So that's a constant field. And there is a field B1, which rotates in the xy plane. It rotates all the time like this. Okay? So in practice, it is difficult to implement a rotating field. It is easier to implement an oscillating field. But then you can split the oscillating field into 2 rotating fields that rotate in the opposite directions. Right? And so the oscillation in the x direction, for example, is the sum of 2 rotations. And then it turns out we can discard one of the rotations that's with the wrong phase and focus on one of them. So physically, an oscillating field can be shown to be equivalent within some approximation to a rotating field. But let's imagine we have this rotating field. And let's imagine that the frequency of its rotation is the same as the Larmor precession frequency of this spin in the influence of the green field in the z direction. So just under the influence of the z field, spin will precess with the Larmor frequency. And now imagine we apply a field that rotates with the exact same frequency. So then what we can do is we can go into the rotating frame of reference. Right? We're going to rotate with the Larmor frequency around the z field. So in that frame, the green field disappears because the effect of that field, we canceled it by rotating ourselves. So if we are sitting in that frame, spin looks stationary until we turn on B1. Is that clear? Yeah? So we went into the frame where we rotate together with the spin as it precesses around the big green field. Yeah? And in that frame, we are always looking at spin in front of us, and it seems that it's fixed. Right? But now, what does the field B1 look like in that frame? It looks like another constant field. That one's not compensated. Right? We're rotating, and the field B1 is rotating with us. So now we are again in the precession situation. So in the rotating frame, it looks like the red arrow, the spin, has to precess under the influence of this field B1. And so it can go from pointing, let's say, in the z direction to pointing in the minus z direction after a certain time. If you wait for a fixed time, which is half of the precession period, we will go from plus z to minus z. And we can actually access any position on this sphere by changing the phase of B1 or the magnitude of B1 and so on. So this is how spin resonance allows us to control the spin qubit or any kind of resonant driving of a two-level system by whatever it couples to, electric field, photons, microwaves, allows us to manipulate a qubit. Okay. So these are the main things you can do based on spin. So here is a situation where you just have a field along z and a spin pointing in a random direction, and so it just precesses along the dashed line. But now we go into the rotating frame, and let's say we start in state 0 here, and we apply a driving field which I draw as being in the x direction, which means that as we rotate with a reference frame set by the frequency of the z field, it looks like the vector B1 points in the x direction. Okay, so we're in a rotating frame. What does it do? It makes a spin precess around the x-axis. And so we can actually flip it from being 0 to being 1 if we wait for half a cycle. Okay? Here's another thing we can do. We can start with 0, and we can just stop it after a quarter of a cycle, and it's going to be pointing in the xy plane. And the xy plane is this plane of equal superpositions. So this particular superposition is 0 plus 1 in our language. Okay. Can also be 0 minus 1. So there's an analogy between the spin and the spinning top. That's also what spinning top does. It precesses. Okay, so these are pretty much the single qubit gates. So how does it look in reality? This is one of my own graphs that I measured at some point to be more comfortable talking about this one. So this is how an experiment looks when try to rotate spin on resonance from up to down for a few times. The experiment goes like this. There is actually a sequence where this qubit, which is a single spin trapped in a semiconductor in a quantum dot, is first initialized always in the same state. For example, state which is 0. And then there is this manipulation phase where a microwave field is applied to this spin for a duration of time tau. And this tau is varied. And it's varied from 0 to 120 nanoseconds in this plot. Okay? And then at the end of this manipulation phase, there is a way to read out this spin by comparing it to another spin. So if two spins point in the same direction, the reference spin and the manipulated spin, they don't want to come together due to Pauli exclusion principle. And if they point in the opposite directions, they come together. And based on this, we can detect whether spin is up or down. Okay? So there is a way to read out this spin. Now let's analyze this curve. This is called Rabi oscillations, after Rabi, who observed them and proposed them. The signal here is some kind of a current measured of these electrons passing through. And if they don't want to pass, the current is low, and that means it's the same as the reference spin. So it means both spins are in the zero state. And if it wants to pass, current is high, and that means the spins are in the opposite state. And initially we have this large oscillation, which then decays until it disappears. So how is this data obtained? First of all, this is current, right? So current in picoamps, that's 10 to the minus 12 amps, right? So that means there is a certain charge flowing per unit time, right? So what is this charge? So single electron is 1.6 times 10 to the minus 19, right? So it's 10 to the minus 19 is a single electron. So if we have a single electron per second, the current is 10 to the minus 19. So we need something about 1,000,000 times faster to get to this range. Right? So that means we have 1,000,000 electrons per second. So we have 1 electron per microsecond passing through some kind of a circuit. Okay? So this already tells you that all of these measurements are ensemble measurements. So with a frequency of 1 megahertz, 1,000,000 times per second, this cycle is being performed. You initialize the qubit in a known state. You have enough time to do that. You do the manipulation for about 100 nanoseconds, which is 1/10 of a cycle. The cycle is a microsecond. And then you read it out, and then the next electron comes. So they go about 1,000,000 per second. And this is quite natural, that you need to always perform ensemble measurements of qubits. That's because a lot of the time what you want to measure at the end is the probability of being in a spin up or spin down state, for example, right? And the highest probability eventually is the answer of your quantum program that you ran. You ran an algorithm, and the highest probability answer is, so you always, in most implementations, you want to run the quantum computation many times, 1,000 times, 1,000,000 times, all this procedure. This is a simple procedure with basically a single qubit gate, but you will have to run the entire algorithm multiple times and then get some statistics on what the answers you get. And from that, you get in. So that's very different from a classical computer, where you can pretty much just do the computation once, and the answer is pretty robust. Okay? In a quantum computer, you have to run it 1,000,000 times. Now we understand what each of these data points stands for, right? So it's basically 1,000,000 measurements or so of the same attempted experiment. Okay? So now what does this decay envelope tells us? So what is it due to? It's due to some kind of decoherence. Right? So if we had a perfectly coherent system, we initialize the qubit and we run this process 1,000,000 times. We always get the exact same answer after the same manipulation time. And we're going to have this oscillation, this Rabi oscillation between the states of 0 and 1 going on forever. So who can tell me how many single qubit flips we can do with these qubits before they decohere? Based on this curve. So single qubit flip is from 0 to 1, or from 1 to 0. When the state is 0, current is low. When the state is 1, current is high. 12, right, so there are 12 periods here, right? So how many flips in 12 periods? 24. Right. Okay. So we could do 24 flips or 48 pi over 2 rotations, right? So go from this to this, because oftentimes that's what you need to do. You want to go from ground state, initialized state, to the maximum superposition state. So those you can do about 50 with this qubit, and you need to do 10,000. Right? So this is not a good qubit. You need to look for better qubits. Okay, 2-qubit gates. You need coupling between two-level systems. So this is a simple example of coupling, dipole-dipole interactions, right? So spin is a dipole, and so sticking with the spin analogy, two spins are two little dipoles, and the magnetic fields that they create will affect each other, and if we manipulate one of them, it can influence the other. So this is one mechanism for implementing a 2-qubit gate. And remember, 2-qubit gates are crucial because they lead to entanglement. Okay. So we can try to see how we can implement using this kind of coupling, or any kind of coupling, a controlled NOT gate. So controlled NOT gate is a gate like this. So here are the states of qubits A and B before and after the controlled NOT operation is performed, and you can see that if qubit A is in the state 0, then qubit B is unaffected. If qubit A is in the state 1, qubit B is flipped. Yeah? B flip if A is 1. So this leads to entanglement. This is how you can do it with spins. So let's say that spin B is in the up state. Okay. Then we first apply this kind of operation, single qubit operation, which is a rotation of qubit A by 90 degrees. So we start with and it's a rotation by 90 degrees around the y-axis. So around this axis. So that means that after 90 degrees from Z, this qubit will go into X. Then we let the two qubits interact. And so one of the qubits is in the X direction. The other one is in the Z direction. And when they interact, it results in a rotation from X to Y. Say you do it for a half of the interaction time. So under the influence of field in the Z direction, then the other qubit precesses in the XY plane and goes from X to Y. And then you apply a final pulse, which is around the X axis, and it's by minus 90 degrees. And that brings the qubit back to Z. Okay, so you perform these manipulations, and it involves a state where one qubit precesses in the field of the other. So if you do it with the other qubit in the down state, then what will happen is the first step will be the same. You initialize in the X direction, but then during this precession time, you're going to precess in the opposite direction to minus Y. Okay, so you see the difference between these two? In the upper column, you precess to plus Y, and in the lower column, you precess to minus Y, because the other spin is in the down direction. And so after performing the same XA minus 90 pulse, you go and end up in the minus direction, so you end up in the state 1. And I think it is confusing because A and B are confused here, right? So this has to be This is a control not gate where control qubit is B, and this is a control not gate where control qubit is A. Okay, that's why it's confusing. So if I say A here, and then, sorry, this is YB, and this is also B, then it makes sense. Okay. So one spin precesses in the field of the other, and depending on the state of the spin that is the control spin, precession is clockwise or counterclockwise. And so what is the 2-qubit gate? The 2-qubit gate is a sequence of these pulses. So Y, B, 90, then interaction, then X, B, minus 90. So 2-qubit gate combines a 2-qubit operation, physical operation where the 2 qubits are allowed to interact, with single qubit rotations. Okay, so this is a one of the simplest quantum algorithms that people have actually performed. And the algorithm is contained here at the top of the screen. It's from this 2009 paper. Actually, the actual useful algorithm is here in the lower panel called Grover algorithm. But both of these people describe these algorithms with these kind of block schemes, and they may look scary at the first, but they basically just tell you the sequence of single and 2-qubit operations. So here is the beginning, is where you initialize the qubit in a 0-0 state. So there's a red qubit and a blue qubit. So the simplest algorithm you can do pretty much with 2 qubits. Okay. Then the 2 blocks with R, Ry pi over 2, Ry pi over 2, are pi over 2 rotations around the y-axis. So these are single qubit gates. Then there is this block Cu, which spans the 2 lines. So that means it's an entangling operation where 2 qubits are allowed to interact, and they become entangled at the output of this. And then they are rotated back, just like we saw. They're projected back onto the z-axis. Right, so they're rotated around different axes. And then the qubits are being read out. So the last block is that they're fed into some readout machine, and it tells you 1 or 0. And this is repeated many times. And in particular, in this state tomography branch, you can see you can rotate around x, y, and by angle 0 pi over 2 pi. So you perform all these different rotations. And the data you get does not look like Rabi oscillations or anything physical. It looks like a bunch of these columns. And these are probabilities, basically the number of times that you got qubit 1 to be in the one state, qubit 0 to qubit 2 to be in the one state, and so on. So here is the kind of a density matrix representation of the final outcomes of this readout, based on the different pulses that you put in. And so by varying the entangler gate and other gates here, you can prepare different quantum states of the 2 qubits, and then by projecting them onto different axes, you can get the probabilities of various terms in the state. So for example, by adjusting the entangler, you can create this kind of state, 0, 0, 1, 1. And you can see that all the weight in these columns is in the corners where you have 0, 0, 1, 1, 0, 0, 1, 1. Okay. So this is how you represent the data in the end. And then you can create 0, 1 plus 1, 0, where the columns will be all in the middle. And these are all different entangled states. Here is the one which is different because there is a minus sign between the two terms in the superposition, and so some of the columns are pointing down. Right? And you get all this data by repeating this sequence thousands of times to get statistics for these columns. Okay. And now this one on the right side of the screen is an actual algorithm which is called Grover algorithm, and it allows you to find the encoded answer. So it goes like this: B, C, D, E, F, G are the different steps in this algorithm. You can see them here: B, C, D, E, F, G are the sequence that you have to run on the 2 qubits. The final answer of this sequence is that the entire probabilities of the measurement have collapsed onto only one of these 16 probabilities. And that's the answer of the algorithm. Okay. Don't want to go too far in the detail of this, but look up Grover algorithm. It's a search algorithm, allows you to find that solution. You can see what I want to show you, that in between you go through different states, where in B you have the initial state where everything is 0, 0. The entire weight of the quantum system is in 0, 0. Then you go into a state where there is a maximum superposition in all of the columns. Right? You can imagine conceptually as you want to find this encoded table, you want to find this one column, and you send your quantum entanglement agents to peek inside every box in the system, right? And then you measure them, and they collapse onto the right one, right? So this is sort of conceptually the power of these quantum computers is in the fact that you don't have to do the full search, flip every lid and find where the treasure is hiding, but you can sort of create a superposition of all states, and then through this entanglement figure out where it was hiding without opening all the cans. Okay? So this is how quantum speedup works. It's supposed to work anyways. All right. So we went through actually initialization, gates, single qubit gates, double qubit gates, readout a bit, and how measurements and algorithms are done conceptually. We have this decoherence left, and here also terminology is borrowed from the nuclear magnetic resonance and spin studies done starting in the 30s. And so basically you have two kinds of processes that hurt the quantum computer. And one is called relaxation, and its time is T1. And the other one is dephasing, and its time is T2. And the two different processes are visually depicted here. So your goal is, like in the panel A, to preserve a certain quantum state forever. And you want this superposition of a qubit states described on the Bloch sphere by this vector chi with certain angles theta and phi. So there are two angles, theta and phi. And T1 are processes that lead to theta going to 0. So in other words, you start with some vector here, and the system relaxes, loses energy to the environment, and goes to the ground state, which is pointing up. Right? In the language of spin, spin collapses onto the direction of the external field because that's the lowest energy. So this is a process that necessarily requires the system to give away energy in some irreversible fashion, and so it is caused by interaction, for example, of spin with a lattice that it sits in, and then the lattice just, through some coupling between electron and photon, takes that energy away, or a photon is emitted and it's gone. And with that energy, information is gone, because that energy was allowing us to keep this superposition. And when it's gone, information is gone. Quantum information is gone. So that is completely irreversible, and you cannot fight against this relaxation. You just need to find a system where this relaxation is long enough. And the other process is T2, and that has to do with angle phi. So it's the phase of superposition of 1 plus 0. So that's also a very important one, because if this angle phi gets scrambled, you also lost your quantum information. But there are some things you can do about that. So it's often called dephasing. It happens due to interaction with other quantum systems. So it is in principle reversible, because you're coupled to a spin nearby, and the two systems get entangled. So you can find a way to unentangle them and get back your quantum information. Okay, so this is, you can do something about it. Although when one spin is coupled to a million other systems, it's very hard to do anything about it. Okay, so dephasing visually looks like this. You want to keep this phase, but with time, it runs away from you, and spin is pointing in another direction in the xy plane. So this does not involve a change of energy. So here are things you can do about protecting against this dephasing. First, how do you measure the dephasing time? Well, you start with spin pointing in the z direction, and then you project it onto the xy plane, where dephasing is the most apparent, because it's related to this angle phi. So you do a pi/2 rotation around the y-axis, and you go from pointing up to pointing like this, and then you wait. You see what happens. And what happens is spin undergoes a free precession in the xy plane. That's normal. But if there is some dephasing, interactions with other spins, that precession is either slower or faster. It's not on the clock. And so if you did this 1,000 times, every time something changed in the environment, you would get one time after a fixed tau, spin pointing in the x direction, another time pointing in the y direction, another time somewhere in between. And then after waiting for a time tau, you do another rotation. You do another pi/2 rotation. And if there was no dephasing, then as a result of this, you would get a pi/2 plus another pi/2. So your spin has to be pointing exactly in the minus z direction. Was pointing up, now going to be pointing down. But with all this dephasing, it will be this rotation will lead to non-perfect results. So, for example, this guy will become this guy, and so on. So, and then if you average all of them together, you will get some vector which is smaller. Maybe still pointing down, but smaller. Or maybe it will be completely zero, average to zero, when the spread of different measurement results is too large. And that means the system has dephased, because you need to measure 1,000 times to get a meaningful result out of a quantum computer. So if every time the rotation frequency is slightly different, you get this dephasing. Okay. So here's what you can do about it. You can do this spin echo trick, and this is a beautiful result, also used in MRI and NMR methods, and also now for quantum computing. You can kind of refocus this distribution. So here is how it works. You put your spin in the x direction like before, then you let the spins evolve, and you can think of this evolution as different spins in an ensemble of 1,000, or different instances of the same measurement. get spread in their rotation. So one time you did this measurement and the spin precessed here, and another time it precessed here, and there is some kind of a spread. Now what you do is you take this spin and rotate it like this. Okay? So the one that was pointing here is now pointing here. And then you let it precess for exactly the same time. So S from A to B, S from C to D. And this fanned out distribution for different instances refocuses, and they all go back together pointing in the same direction. Why is this? It's because each one of these spins in the fan precesses its own frequency determined by the local situation and its environment. And so if you let it precess out of sync for a time tau, and then flip it here and let it precess for another time tau, it will go back in sync. So this fan will refocus, and that's called spin echo. And so by this, you can recover coherence and prolong the storage time of the quantum state. So this is a trick that you can always play. Now, in the last 5 minutes or so, I'll give you a rundown on some of the things that people have tried to use as qubits and quantum processors. Okay. So one of them is actually a molecule. So wouldn't it be awesome? You make a complicated molecule which has many spins, and that is your quantum computer, the entire computer. And then you manipulate that molecule with NMR techniques. And so people have actually done it. So this is a test tube containing a gazillion of these kind of molecules. And each one of these molecules is a quantum computer. So here is one of the implementations with 7 different qubits. In this case, qubits are nuclear spins in this molecule. So they are manipulated by nuclear magnetic resonance, which is a technique that works in the megahertz frequency. Okay? So here is 1, 2, 3, 4, 5, 6, 7 spins. Here's the kind of algorithms people run on them. So they are different NMR pulses operating at different frequencies corresponding to different spins. And what they were able to do with this is a quantum algorithm known as Shor's algorithm. Shor, which is considered a landmark algorithm which allows you to find prime factors of an arbitrary number. Okay? So that's the sort of the poster example of a quantum algorithm. Turns out it's really hard to find prime multipliers of a long number. And this is how, for example, our credit card encryption works, among other things. And then the quantum computer should be able to do it in no time. Right? It takes exponentially long for a classical computer, and then a quantum computer can just do it. Okay, so they were able to do it, but with a number 15. Okay, so this back in 2001, they factored 15 with this molecule, with a single molecule, into 3 and 5. And I think what they actually got is something like 4.8 and 2.7 or 3.3 or so. Okay. All right. So there's been some progress since then, but this was maybe at least conceptually. Here you have 7 different lines, and you apply all these pulses to each of these frequencies. These 3 lines mean different frequencies because each of these spins works at a different frequency, different energy spacing, right? And then you carefully time the waiting times in between and so on, and you run a quantum algorithm. Okay, here are trapped ions. I already mentioned them to you in the beginning. This is how they look. This is already a bit dated. Because this one has 4 of these ions. You can actually image them. They fluoresce, and you can resolve where they're trapped between electrodes. Here's another example of 4. Trapped between in an electrostatic and magnetic trap, hanging in vacuum, right? And each one is approximated as a 2-level system. You interrogate them with laser light, and you can do this very nice Rabi oscillations that can doesn't look like they dephase. Actually, these are Ramsey fringes, but this is the experimental setup to control these 4 atoms. There is a vacuum chamber buried in the middle of the mess, and then the rest are a bunch of different lasers that hold them together and control them. The way you take these pictures is by a CCD camera. You can actually see the individual atoms in laser light. Yeah, you can read out their states by imaging them at the end of the computation. So when they fluoresce, then they're in, let's say, state 1, and when they don't fluoresce, then they're in state 0. You can tune it to some dark transition. So here is an example of a qubit, so 8, and this now we're moved into 2006. By now, I think they can do about 40. At least they can control 40. I don't know about entanglement of all of them. And the experiment is even more complex. It doesn't fit on one such table, but requires a whole lab. Okay. Superconducting circuits, I'm just going to skip because you're going to have a whole lecture on this stuff, but this is how they look. A bunch of superconducting lines with some junctions. Like these are junctions. And you can do Rabi oscillations, and these are some of the best qubits right now. Spin qubits can be done. I already showed you one trace based on a nanowire, but here are some implementations. Like this is inside a 2DEG, which you have seen, had a whole couple lectures on it. And in this 2DEG, 2 quantum dots are defined like this. And remember, you need 2 quantum dots to read out. The one is to read out the other. And so, but it also gives you sort of 2 spin qubits next to each other. And people have extended it to 4 by now, even 8. But the structure also becomes more complicated because this is how many electrodes you need to confine to. So to confine 416, you need even more. And you can do a few Rabi oscillations with these. And now this has been improved also quite a bit beyond this. Here is a single impurity in diamond, which is a popular quantum system. So this is a diamond crystal lattice, and one of the sites is empty, replaced with nitrogen, and the nearby is empty, which is V, vacancy. And turns out that this defect has a complicated level structure, but 2 of the levels here can be thought of as a spin qubit. Okay? They have different MS projections. You can define a qubit based on these. And so these are pretty good qubits. And sometimes people use nanodiamonds that they position in optical cavities to enhance the coupling to laser light. And sometimes they use a bulk diamond and find a defect in a diamond. The question is, how can you scale this, right? So ideally you want an array of defects, which you have 1 million of them with the exact periodicity and so on. So this has so far been out of reach. Okay, there is some work on long-distance communication, and banks are interested in this because this is now about flying qubits. So if you send information encoded by quantum degrees of freedom, it's impossible to eavesdrop on this channel because as soon as somebody measures your transmission between Geneva and Lausanne here, for example, then you change the quantum state by measurement by the third person, and then you know that somebody's been listening. Okay, so this is supposed to be perfectly secure. There is a company that builds these kind of machines that send entangled photons. A distance of here is 1 one of these nodes called Alice, and here on the horizon is Bob, a couple hundred miles apart. I've also met a guy who calls himself a quantum pirate, and he is dedicated his research to hacking these machines. Okay, so yeah, so this guy, his name is Vadim Makarov. He exploits some of the weaknesses of this because this is not a perfect quantum cryptography machine because they send more than one photon per burst. And so they're cheating a bit. And this allows them to send a few more photons in the same beam and then get some piece of information from the line. So if they were really sending single photons, they would be impossible to crack. But the current implementations are still crackable. Okay, maybe one slide about what's coming. So all of this is nice, and there are different ideas people have to build qubits. But when people talk about scalability and protection against errors, it seems this threshold for error correction that you need to be able to perform thousands and thousands of operations without error-free seems to be a heavy burden. And to circumvent that, people came up with this concept of a surface code. And the surface code allows you to lower the threshold for error correction by a few orders of magnitude. So it means you can have a lot more errors, right? And still run a quantum algorithm. But the price you pay is that this is a single qubit. Okay? And each dot here is a physical qubit, so red and white dots. And these green and yellow shapes are representing single two qubit gates that you have to constantly run on a constant cycle between these qubits to keep them coherent. Okay? So this is this surface code involves measurements on plaquettes, which is 4 different measurements in the basis of X, in the basis of Z, and this is a extremely complex structure. So one of these crosses involves these kind of entanglement operation and single qubit gates for 4 different qubits. And if you want to encode qubits in this kind of surface code, you turn off one of these measurements. So this empty space becomes then your qubit. Okay, so am I blowing your mind already, or should I keep going? So all of these dots are things like individual spins or individual superconducting loops, right? And all this infrastructure is needed to keep the surface code going. But then if you want to encode one single bit, 0 or 1, of quantum information, you turn off one of these plaquettes. You stop measuring there. And that's a single qubit. So this way, a single qubit involves something like a minimum of 40 physical qubits, and that's called a logical qubit, then, which involves 40 physical qubits. And people think that if quantum computing will ever work, that's the only way it can work. That's the current thinking for the last 5 years. Okay, so we have to build this kind of crazy, crazy circuit. Okay, so these are different ways that you can manipulate these qubits. So then you have all these holes in 2D, and then you have to move them around each other to perform qubit operations, like single qubit operations and double qubit operations. These are the kind of, this is the C0 gate, for example. So you have these holes, and then you have to move them around each other. This is a single qubit gate, and so on. Okay, so some people think it's possible because the number of qubits you need is just 1 billion, and we kind of have that already on the latest Intel chip. So at least we can build 1 billion qubits. Then to keep them all controlled, that's another story. So what's the summary? Can a quantum computer be built? Maybe, if we really want to. Okay. So far we really want to, and so we keep going.